Hello everyone and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
Okay, we've been talking a lot about the dispersion, but we know the dispersion is just the bucket we pour the electrons into.
Yeah, so we really need to think about which states in the dispersion are actually occupied.
To that end, we're going to do some rather important bean counting in this episode that addresses how our electrons fill our bands.
I know that we plot band structures from k equals minus pi over a to pi over a, and the line is really only semi-continuous.
And by semi-continuous, you're saying that the line is actually composed of a series of discrete k points, each separated by 2 pi over L.
Yeah, so in 1D, each band spans a reciprocal distance of 2 pi over a. Then the number of discrete k points in the band must be equal to the number of unit cells, n.
Yep. How many electrons can the band hold then?
2n, since we can put a spin up and a spin down electron in each mode.
And depending on how filled these bands are and how they're arranged, we can get 4 different types of materials. On the two extremes, we have metals and insulators. In between, we have semimetals and semiconductors.
And the shading along the bands indicates the occupied states?
You got it. We could also show this in terms of the density of states.
Alright, so let's test this with some real-world examples.
Okay, how about carbon in the diamond structure?
Well, I know carbon has 4 electrons, so we're going to have an even number of electrons, regardless of whether we consider the primitive or the conventional cell. Since I know diamond is transparent, I'm going to guess that there's a big gap between a filled band and the next unoccupied band.
Exactly, and we call diamond an insulator. How about if we looked at gallium arsenide?
Well, together, gallium and arsenic bring 8 valence electrons to the table. So again, we have an even number, and I'm going to go with an insulator, or maybe a semiconductor.
That's a reasonable guess, and it turns out gallium arsenide is a semiconductor with a gap between the filled and empty bands of about 1.4 eV. Predicting this for gallium arsenide isn't so terrible, since we think of it as a diamond-like semiconductor with sp3 bonding. Let's move on to lithium.
Okay, well that's easy. I know lithium is group 1 and has a total of 3 electrons. Because 2 of them are core states, the valence band is half filled, so I'd guess a metal.
Sure, but then let's add an electron. Why is beryllium a metal?
That's weird. So we've got 2 electrons per atom, so regardless of the crystal structure, we're going to have an even number of electrons. I want to say that the bands will be fully filled, but that doesn't agree with beryllium being a metal.
I'm just going to let you drift in the breeze.
Fine, I don't need your help anyway. So beryllium's 2p orbitals must have dropped down and mixed with the 2s orbital, leading to multiple bands at the Fermi level.
There you go. We can actually see this in the calculated dispersion.
Actually, seeing this dispersion, I think I can take this a step further. What's the crystal structure of beryllium?
Hexagonally close packed.
Okay, that means it's got 2 atoms in its primitive cell, and thus we're going to dump 4 electrons into the bands. You might think this should fill the first 2 bands and give us the highest energy electron back at the gamma point.
Sounding good so far.
And in that case, the next lowest energy state would also be at the gamma point. So when the unoccupied band drops down into the occupied band, the overlap starts at gamma. And you can see this in the calculated dispersion. Is this the same sort of behavior we'd see in other metals?
I'd say this is a really clean example, actually, since we're only dealing with the 2s and the 2p orbitals. Let's take zinc as a second metal example.
Okay, so we're looking at the far right side of the transition metals. Again we see that there's an even number of electrons.
And when we look to the calculated dispersion, the whole thing's a mess, with many bands at the Fermi energy. So now we can see that in real systems, we need to be careful about predicting how we fill our bands.
Okay, so what would a semimetal look like?
Well, cadmium oxide is a nice example of a semimetal. Here we can see how the Fermi level splits between 2 bands.
And we're calling it a semimetal because there's no crossing of the two bands at the Fermi level.
Exactly. You can see this further by looking at alloying with calcium oxide. As we alloy cadmium oxide with calcium oxide, we can pull these bands apart and end up with an insulator.
Okay, so let's do a recap. Today we introduced metals, semimetals, semiconductors, and insulators. In general, I'd say that classifying materials is pretty easy if you know the dispersion, but that it's pretty tricky to predict in advance.
Luckily, electronic structure calculations are getting more and more common. So common that we'll have a week on them later in the semester.
Okay, so how about some questions to ponder? Let's start with zinc oxide as a sunblock material. Can you connect the band structure to its use in protecting us from UV light?
So here's a two-part question on the band structure of bismuth telluride. First, simply what type of material is it?
And as you might imagine, the highest occupied electronic states are going to matter a lot for electrical conductivity. How many maxima does the valence band edge have in the first Brillouin zone?
Okay, finally let's think about metals. Here's the band structures of aluminum and copper. Why are these metals, and why do the dispersions look so different? Okay, that's a wrap. Thanks for watching today's installment of Solid State Physics in a Nutshell. Next week, we'll be taking a look at the electrical properties of intrinsic semiconductors. See you then.